Behold the Great Pyramid of Giza. The entire structure was assembled with a precision that still baffles modern engineers. And here's the question that has haunted archaeologists, engineers, and historians for centuries. How exactly was it built? You might assume we have the answer by now. We don't. In fact, every major theory proposed so far has a critical flaw, and some of the newest ideas may be the most flawed of all. Today we're going to walk through every major theory: ramps, internal systems, hydraulic lifts, counterweights, and the new 2026 Unbuilding proposal, and show precisely where each one breaks down. Then we're going to propose something that mainstream archaeology is not ready to discuss, that the answer has been hiding in plain sight all along, and it points to a civilization far more advanced than anything in the official timeline. Stay with me, because by the end of this video, the pyramid you thought you knew will look completely different. The ramp problem, bigger than the pyramid itself. The oldest and most intuitive explanation is the ramp theory. Workers drag enormous stone blocks up massive earthen ramps to stack them, course by course, until the pyramid reached its final height. Simple, logical, except when you run the numbers, it collapses almost immediately. For a straight external ramp to maintain a functional slope shallow enough for workers to haul heavy loads, generally under 10 degrees, you would need to stretch over 2 kilometers, 1 mile in length. To put that in perspective, building that ramp would have required more raw material than the pyramid itself. And yet, despite decades of excavation across the Giza Plateau, not a single trace of such a ramp has ever been found. No compacted earth, no retaining walls, no foundation remnants, nothing. For Egyptologists, this absence of evidence has become one of the field's most uncomfortable silences. So what about a spiral ramp, wrapping around the pyramid's exterior as it rose? This idea solves the length problem, but creates new ones. Workers dragging sleds up a narrow spiral ramp would have no clear view of the pyramid's edges, making it nearly impossible to maintain the precise geometry that the structure demands. And with one ramp serving as both the upward and downward path, traffic congestion alone would have crippled construction timelines. External ramps, whether straight or spiral, are now widely regarded as logistically implausible, particularly for the upper third of the pyramid. That top section, the final 160 feet of height, is where every theory begins to unravel, if not fall apart. Getting hundreds of thousands of tons of stone to those heights, with the precision the structure requires, is the central unsolved challenge of pyramid construction. Engineers call it simply the biggest ramp debate in Egyptology. The internal ramp, a clever idea that the evidence doesn't support. In the early 2000s, French architect Jean-Pierre Houdin proposed an elegant solution. What if the ramp was inside the pyramid all along? In his model, an external ramp handled the construction of the lower third, while simultaneously an internal spiral ramp, about 6 feet wide, with a gentle 7% grade, was being built within the pyramid's outer shell, allowing workers to reach progressively higher levels from the inside. It's a genuinely clever hypothesis, and it attracted serious attention. But then came the scams. The scam pyramid project, led by Japanese and French physicists, used Muon tomography to peer deep into the Great Pyramid without touching it. What they found was remarkable: a previously unknown 30-meter void above the Grand Gallery and a 9-meter corridor near the north face. What they did not find was any evidence of a spiraling internal ramp. Beyond the scan results, there are practical objections. How would thousands of workers manage heavy stone traffic inside 6-foot-wide tunnels with no ventilation. How would it coordinate upward and downward movement in such confined spaces? Critics argue the internal ramp theory trades one set of impossible logistics for another. The unbuilding theory, building more to build less. In January 2026, a new hypothesis entered the conversation, one that initially sounds counterintuitive, but has been gaining attention precisely because it tries to tackle the infamous apex problem. How was the very top of the pyramid constructed and finished to such precision? The proposal goes like this. Builders first constructed an oversized, rough trapezoid stabbed mass, larger than the intended final pyramid. They then carved the excess stone away from the outside, sculpting the precise, smooth pyramid surface in a process of deliberate subtraction. The removed stone, the theory suggests, was not wasted, but recycled to build other structures on the Giza Plateau, including the second and third pyramids. It is an imaginative idea, but under engineering scrutiny, it does not hold up. First, consider the fundamental paradox at its heart. If we cannot explain how the ancient Egyptians lifted 2.3 million blocks to build the Great Pyramid, then we certainly cannot explain how they first built an even larger structure and then dismantled millions of blocks from it. The unbuilding theory does not eliminate the ramp problem, it amplifies it. More stone would have needed to reach greater heights before any carving could begin. In terms of raw labor and logistics, this approach certainly requires more total work than simply building the pyramid correctly the first time. Then there is the archaeological evidence embedded within the pyramid itself. Surveys by pioneering Egyptologist William Matthew Flinders Petrie revealed that the internal limestone courses are laid in precisely uniform horizontal layers, with consistent leveling across the entire structure. The block placement reflects deliberate, planned geometry from the very first course. If the pyramid had been roughed out as an oversized, irregular mass and then sculpted into shape, the internal blocks will likely be randomly oriented and irregularly trimmed, not arranged in a clean, load-bearing horizontal courses we actually see. There is also the question of the casing stones. The Great Pyramid's original outer surface was covered in brilliant white Tura limestone, a material quarried across the Nile, transported by boat, and shaped to fit with amazing precision. If the pyramid was carved down from a rough core, those casing stones would need to have been cut directly from Giza limestone in situ. But that is not what happened. The casing stones are a distinct imported material quarried elsewhere and placed as individual fitted blocks. The outer surface was not carved from a larger mass. It was constructed. Finally, think about a recycling claim that the blocks removed from the oversized first pyramid were transported to build the second, then the second to the third. The base of the Great Pyramid sits about 10 meters lower than the second pyramid at Giza. Moving salvaged multi-ton blocks uphill from one pyramid site to another after already hauling them down from the first structure would have generated tremendous additional labor. And the third pyramid is located a considerable distance away. The pyramid core limestone was not a precious or scarce material. It came from the plateau bedrock directly underfoot. There was no logical reason to recycle it when fresh stone was readily available at each site. Most engineers and archaeologists conclude the same thing. The unbuilding theory would require more total effort, not less. If ramps don't work and the unbuilding construction also doesn't work, could the answer be something more radical? Water, counterweights, and the limits of ingenuity. The hydraulic lift theory proposes that the ancient builders used water pressure and the internal shaft systems to literally float stone blocks upward through channels inside the pyramid. Supporters point to evidence at the step pyramid of Djoser at Saqqara, where a 2024 study published in ResearchGate identified structural features consistent with a water regulation and treatment system, suggesting hydraulic technology was within the ancient Egyptians' grasp. But between theoretical possibility and practical application lies an immense gulf. The pyramids are not waterproof. Their limestone blocks are jointed without mortar that's not capable of sustaining water pressure. The step pyramid of Djoser is located on the Saqqara Desert Plateau, rising 17 to 25 meters, 55 to 80 feet above the modern Nile flood terrace. The Giza pyramids sit approximately 60 meters, almost 200 feet above the Nile, much higher than any natural water source. And the physics simply do not cooperate. A 2-ton stone block does not float. Water pressure sufficient to elevate such a mass would require containment systems, pipes and chambers, capable of sustaining incredible force. There is no evidence the ancient Egyptians possessed the materials or sufficient water remotely capable of this. Then there is the counterweight pulley theory, which reinterprets the Grand Gallery as a mechanical lifting mechanism. In this model, heavy counterweights would slide down the Grand Gallery and the ascending passage, generating force that through a pulley-like system in the antechamber could raise stone blocks to higher levels. It is an intriguing reading of the Grand Gallery's unusual architecture, but the antechamber is a notably small space, roughly 5.6 meters long, 2.1 meters or 6.7 feet wide, and 3.6 meters high. The idea that this narrow transitional room served as a pulley mechanism for hauling the pyramid's heaviest blocks, including 70-ton granite beams, strains credibility. More pointedly, the system is located in the lower portion of the pyramid, precisely where lifting is least problematic. The central engineering challenge has always been the upper third. A counterweight system based in the lower interior offers no solution to that. And crucially, if this construction method was so effective, why was it apparently never used in any other pyramid? The Great Pyramid stands alone in possessing a Grand Gallery, but no other pyramid shows any comparable internal sloped structure that would suggest a similar building approach was repeated. If the Grand Gallery was used as an efficient lifting mechanism, why did no other pyramid in Egypt adopt it? So, how was it built? We're left with a perplexing situation. No ramp, internal or external, satisfactorily explains how 2.3 million stone blocks were moved and placed, especially in the upper reaches of the structure. The hydraulic lift and counterweight theories each have fundamental flaws that their proponents have not resolved. And the newest hypothesis, the unbuilding approach, required more labor than a conventional model it was designed to replace. What does this tell us? It tells us that either our understanding of ancient Egyptian organizational and engineering capability is still seriously incomplete, or that some element of the construction method has been lost entirely, leaving no archaeological trace. Perhaps the answer involves a combination of techniques we have not fully reconstructed. Perhaps future scanning technology will detect voids and structural clues that the Muon tomography missed. Or perhaps, and this is the thought that keeps researchers up at night, the Great Pyramid was built using a method so unexpected, so outside the framework of assumptions we bring to the question, that we have not yet been willing to seriously consider it. Before we chase more exotic explanations, there is one theory that deserves serious attention, not because it's the most dramatic, but because it's the most testable, and the test results are truly surprising. The concrete hypothesis, casting the impossible into place. Researcher Joseph Davidovitz proposed decades ago that the pyramid's stone blocks were never quarried or lifted at all. Instead, he argued they were cast, poured in place from a limestone-based geopolymer concrete, similar in principle to the concrete we use today. Mix the right minerals together, pour them into a mold, let them harden, and you have what looks, from the outside, indistinguishably like a natural limestone. This idea has been treated with deep skepticism by mainstream Egyptology, but the material science tells a more complicated story. Multiple independent analyses using X-ray diffraction, electron microscopy, nuclear magnetic resonance spectroscopy, paleomagnetic investigation, and plasma torch testing have repeatedly found that both the core stones and casing stones of several pyramids contain characteristics more consistent with a manufactured, concrete-like material than with naturally quarried limestone. One study even identified silicon dioxide nanoscale spheres embedded in a stone matrix, a feature associated with high-temperature or chemically processed materials, not natural geological formation. The Egyptological establishment has not accepted these findings, but they have not been cleanly refuted either. The debate remains open, and the material evidence is harder to dismiss than its critics often acknowledge. A radical extension, the mind waste theory. In September 2021, building directly on a concrete hypothesis, I proposed a new and far more provocative idea. What if the pyramid was not a tomb, a power plant, or a monument at all, but an industrial waste storage facility? My hypothesis goes like this. The Giza Plateau was once a large-scale mining operation run by a technologically advanced civilization that predates dynastic Egypt. After the ores were extracted, the remaining waste, crushed rock, tailings, chemically contaminated debris needed to be safely contained and immobilized. The solution was elegant and permanent. Cement the waste into concrete blocks, stack them into a stable mass, and seal the contamination in place indefinitely. This process has a precise modern analog. Today, mining operations have started to manage hazardous tailings by mixing them with binding agents and storing them in engineered containment structures, sometimes called paste tailings or cemented waste rock fills. The goal is just what the pyramid achieves: chemical stabilization, long-term containment, and structural permanence. Several features of the pyramid align with this interpretation in ways that are difficult to explain otherwise. The pyramids are 99.9% solid, with minuscule internal openings or no openings at all, as if the construction goal was to pack in as much locally sourced artificial material as possible. The internal passages are unusually narrow and low, not remotely suited for human access or ritual use, but entirely consistent with the internal drainage channels or monitoring access points in a sealed containment structure. The pyramid's gargantuan mass, distributed in precise horizontal courses, is structurally ideal for long-term load-bearing stability over geological timescales. And the Giza Plateau itself shows geological and geochemical characteristics, such as large vertical shafts, traces of metal ores, and underground caves consistent with the historical mining activity detailed in earlier videos linked below. What modern construction actually tells us. Here is where the argument becomes compelling. Set aside ancient methods for a moment and ask a different question. If we were going to build a Great Pyramid today, how would we do it? We would not use ramps. We would not carve and haul 2.3 million individual stone blocks. We would pump concrete. Modern concrete pumps routinely move 100 to 200 cubic meters of a material per hour vertically over distances exceeding 200 meters. The Great Pyramid originally stood 146.6 meters tall. Pumping a concrete mixture to its apex would be, by today's standards, an unremarkable engineering task. With tower cranes, climbing formwork systems, and laser leveling equipment, the structure of the pyramid's volume, approximately 2.6 million cubic meters, falls well within the range of modern mega projects. Large dam projects regularly involve 10 to 20 million cubic meters of concrete. The pyramid is massive by ancient standards, but unexceptional by modern ones. A realistic construction timeline using today's methods will be somewhere between 2 and 4 years. This comparison is not just an interesting thought experiment. It reframes the entire mystery. If conventional ancient construction methods cannot adequately explain the pyramid, but modern concrete construction methods can, and if the material evidence suggests the stone is manufactured rather than quarried, then the question shifts from how did it move the blocks to what kind of civilization were they? Why blocks, not poured layers? A reasonable objection arises. If the builders of old had concrete technology, why cast individual blocks? Why not pour the entire structure in continuous layers? The answer is straightforward structural engineering. Pouring a structure this size in continuous layers creates cold joint formation. The interface between a new layer and an already hardened one becomes a plane of weakness, since new concrete does not naturally bond to the cured concrete. Large continuous pours also generates intense internal heat during curing, producing steep temperature gradients that cause deep cracking, catastrophic for a structure meant to last millennia. Dry-stacked concrete blocks solve both problems. Dry-stack mine waste storage facilities are dynamic structures built in multiple phases over the entire life of a mine. Dry stacks grow incrementally to accommodate the continuous production of waste. Individually cast and cured blocks eliminate cold joints and thermal stress events. They cure faster and are easier to maneuver and stack. The small gaps between blocks act as natural expansion joints, allowing the structure to adjust to temperature changes without transferring stress across the whole. And staggered, interlocking courses distribute loads across multiple units simultaneously, providing excellent resistance to lateral forces over time. Casting individual blocks and dry stacking them is not a primitive workaround. It is, for a permanent massive mine waste facility, the smarter engineering choice. Precision without the puzzle. One final observation is worth sitting with. Among the pyramid's most celebrated mysteries, it's its superb geometric precision. The near-perfect alignment of its faces, the exact proportion of its base, the seamless fit of its casing stones, and its subtle concave faces, a deliberate inward curve on each side so slight it's invisible at ground level but detectable from the air. For researchers who assume the pyramid was built from individually quarried and dressed stone blocks, this precision is almost inexplicable. Achieving it would require thousands of workers making thousands of individual cutting decisions with no margin for accumulated error. But if the blocks were cast in concrete using formwork, essentially reusable molds, the precision is not mysterious at all. It's a natural consequence of the process. Formwork controls geometry. A well-made mold produces precisely dimensioned blocks. The ultra-precise casings, rather than representing some exceptional feat of ancient stone cutting, would simply reflect the geometry of the formwork system used to shape the outer surfaces. The pyramid's famous precision, in this rating, is not evidence of superhuman effort. It's evidence of good engineering. a question worth taking seriously. The Great Pyramid has resisted satisfactory explanation for as long as humans have been asking the question. Every conventional theory, ramps, internal construction systems, hydraulic lifts, counterweight pulleys, fails at some critical point. The newest proposal, the unbuilding approach, arguably creates more problems than it solves. But the concrete hypothesis extended into the mine waste storage theory does something the others do not. It resolves multiple anomalies at once. It explains the artificial material composition of the stones, the impracticality of conventional lifting methods, the narrowness of the internal passages, the pyramid's almost completely solid feature, the structure's extraordinary longevity, and its geometric precision, all within a single coherent framework. The Great Pyramids have stood for 4,500 years. They have outlasted every civilization that followed it. If the methods we confidently attribute to dynastic Egyptians cannot account for how they were built, but the modern industrial methods can, then we may need to ask a far more unsettling question. Not how were they built, but who exactly had that kind of knowledge to build them. This is my 100th long video. I hope you liked it. If you are new to my channel, please subscribe and share with others. You can also support me on Patreon, which is a monthly charge, or on Buy Me a Coffee. I appreciate your support. This is Curious Being. I'm Tina. Thanks for watching and see you next time.